they will form that planar kind of shape. So now we have s orbital plus 2p orbitals. These are 2p orbitals. So when they combine, they will form sp2 hybrid orbitals, as you can see in that diagram. Then we have sp3 hybridization, where we combine one s orbital and 3p orbitals. That means that central atom must form a maximum of 4 bonds. And this one is seen in methane. Carbon is supposed to form 4 bonds with hydrogen. That means carbon must have 4 unpaired electrons. So as you can see, atomic number of carbon is normally 6. So the first 2 electrons are in the first shell, 2 electrons in the second shell. Then we have 1 in the first P, another one in the second P. Because remember, we are supposed to follow Hund's rule. So we fill those degenerate orbitals with 1 singlet electrons first before we start pairing up. So we shall have 1, 2 here. So to enable carbon to have 4 unpaired electrons, it means we shall have to promote 1 electron from the 2s orbital to the 2p orbital. So this electron will come here, it will be promoted, so that 2s remains with 1 electron. Then these other, the 2p orbitals, each has 1 unpaired electron, so it becomes 3. So now we combine 2s and 2p to form a hybrid orbitals. So we shall have 1, 2, 3, 4. So this one is 1s combining with 3p 2p orbitals, so that we have 1s with 3p orbitals. So this type of hybridization is called sp3 hybridization. So thus, using valence bond theory, each of the carbon sp3 hybrid orbitals can overlap with the 1s orbital of a hydrogen atom to form a bonding pair of electrons. So you can see 2s, then this one are 2p orbitals. So 1, 2, 3, there are 3, then with 1s. So when they combine, they will form this kind of shape. It's called tetrahedral. So they are normally identical. We have 1, 2, 3, 4. So these are identical hybrid orbitals. So now, you can see now in water, the central atom is oxygen, which is supposed to form 2 bonds with hydrogen. So the atomic number of oxygen is normally 8. So when you write, when you distribute those electrons in various orbitals, you can see 1s will have 2 electrons, 2s, 2, then 2p, the first p orbital has 2, the second p orbital has 1 and 1. So that means in that manner, oxygen can still form a bond. So we need to hybridize directly. We don't promote any electron because already the p orbitals have 2 unpaired electrons, which will participate in the bonding with the 2 hydrogen atoms. So we simply hybridize the 2s orbital and 2p orbitals so that we come up with sp3 hybridization, 1s and 3p orbitals to form sp3 hybridization. So in that case, we shall have 2 lone pair of electrons which will not participate in bonding, but these other last 2 unpaired electrons will now participate in bonding with hydrogen atoms. So that's, you can see we are hybridizing 1s and 3p, so we shall form sp hybrid orbitals. So there are 1, 2, 3, 4. So the 2p orbitals will contain lone pair of electrons. You can see we have a lone pair here and a lone pair here. So the other 2, these ones, will now participate in bonding with hydrogen, as you can see in that diagram. So this one's a tetrahedral kind of shape. If we use valence shell pair electron repulsion method to term the geometry, so this one becomes a tetrahedral shape. It has 1, 2, 3, 4 vertices. Then we look at hybridization involving the d orbitals. So that means fluorine, pentafluoride. So fluorine is supposed to form a total of 5 bonds. So when you look at phosphorus has 5 valence electrons. So you can see 3s has 2 electrons, then 3p has 3 unpaired electrons. So that means we need to promote 1 electron from 3s to 3d, so that we have 5 unpaired electrons. That's why this kind of hybridization is called s, p3 and d hybrid orbitals. It is involving an s, 3p and 1d. That's why it's called sp3d hybrid orbitals. So those 5 orbitals are normally identical. So it is 1, 2, 3, 4, 5. So they will arrange themselves in such a way that they form what we call trigonal bipyramidal. So you can look at that shape. So similarly, hybridizing 1s, 3p and 2d orbitals yields a 6 identical hybrid sp3 d2 orbitals. This would be oriented in an octahedral geometry. So if you have a central atom which is supposed to form 6 bonds, then it must undergo sp3 d2 hybridization, just like the way we considered in the previous examples. If you look at those geometrical shapes in the previous tables, you have some compounds which can undergo such a kind of hybridization, where they form a maximum of 6 bonds. For example, if you look at this compound here, this one, silicon, S, sulfur hexafluoride, it has a total of 6 bonds. So that molecule can undergo what we call sp3d2 hybridization. So it forms an octahedral kind of shape. So now steps in predicting the hybrid orbitals used by an atom in bonding. First of all, you draw the Lewis structure, determine the electron pair geometry using the valence shell electron pair repulsion model, then specify the hybrid orbitals needed to accommodate the electron pairs in the geometric arrangement. So this one is the Lewis structure of ammonia, as you can see. A nitrogen has 3 covalent bonds, and you put their lone pair of electrons. This is a Lewis structure of ammonia. So if you use the valence shell electron pair repulsion to determine this geometry, it's called tetrahedral, because we also include this lone pair of electrons, 1, 2, 3, 4. So you assume it is a tetrahedral kind of shape. But if we use now the real geometry of the structure, is called trigonal bipyramidal. So the tetrahedral arrangement indicates 4 equivalent electron orbitals. So that one, that's just showing how hybridization takes place in ammonia. So remember nitrogen has 7 electrons in total. So when you write electron configuration, you will find that that nitrogen will have the first 2 electrons occupying the s orbital, the second 2 s, and the last 3 in p orbital. So that means in this manner, nitrogen is supposed to form 3 covalent bonds with the hydrogens, 3 hydrogens. So each will contribute 1 electron. So we hybridize S and P to form sp3 hybridization. So in that case, one orbital will have a lone pair of electrons, but the 3 others will now share wrap electrons with 3 hydrogen atoms. So you can see this lone pair of electrons is here. Then we have those 3 unpaired electrons now sharing with hydrogen, one here, another one here, then the last one is shared here. So this kind of shape is called tetrahedral if you use valence shell electron pair repulsion method. So we include this one, it's 1, 2, 3, 4. So it is oriented in 4 different directions to form a tetrahedral kind of shape. So that table shows valence electron pairs, the number of orbitals, and hybridization. If that geometry is linear, it means it has 2 orbitals participating in the bonding, so it is sp hybridization. If it has 3 orbitals participating in bonding, then it is sp2 hybridization. If it has 4 orbitals participating in bonding, it is sp3. If it has 5, sp3, then T. If it has 6 orbitals participating in bonding, it is sp3. That means these are the number of bonds, covalent bonds, which are formed. It determines the type of hybridization. Then these are just the geometry: linear, trigonal, planar. Linear, like in beryllium difluoride, beryllium with 2 fluorine atoms. Then beryllium with 3 fluorine atoms, trigonal, planar. Then this one is like in methane. Methane forms 4 bonds. So the central carbon undergoes sp3 hybridization. Then in phosphorus tetrafluoride, it has 5 fluorine atoms. So it's called trigonal bipyramidal. So it undergoes this hybridization. Then if it has 6, like sulfur hexafluoride, it is octahedral. It will undergo sp3d2 hybridization. So that lecture ends there for now.